short. Okay, I was just, you do it. I'm happy to hear whatever you have to say. Let's just turn this off. I know, I'll just use my phone.
Uh, Good afternoon, everyone. A very warm welcome this afternoon to the special colloquium by Professor Subir Sachdev. So Professor Subir Sachdev is the Herschel Smith Professor of Physics at Harvard University. He did his Bachelor of Science from MIT, and he did his PhD in Theoretical Physics from Harvard University. And he has been elected to the National Academies of Science both in India and in the United States, and as well as Royal Society in the UK. He's the recipient of several awards, including the Dirac Medal from the International Center of Theoretical Physics and Lars Onsager Prize from the American Physical Society. Professor Sachdev has made significant contributions to the theory of diverse varieties of quantum matter and their behavior near quantum phase transition. And this famous sachdev-ye-kitaev model, as you can see, is after his name. And he has written several very famous books like The Quantum Phase Transition, Holographic Quantum Matter, and Quantum Phases of Matter. So I welcome Professor Subir Sachdev to give the special colloquium.
Well, okay, thank you very much. It's really a pleasure to be here at RRI. I've been here for a few weeks, and but it was nice to meet everybody here at the Academy Guest House. And one thing you forgot to mention, I went to school just a few miles from here on Museum Road in Bangalore, where I was earlier today. Okay, so it's a pleasure to be back here. All right, so in this talk, I'm going to give a kind of a survey of things I've been working on over the past few decades. And I've tried to encapsulate some of the main ideas in some simple pictures and give you a sense of where the fields are going and what needs to be still understood. Okay, so a lot of this work is motivated by a class of superconductors called cuprate high-temperature superconductors, which were discovered in 1986, 87, when I was a young postdoc. And they created a lot of excitement because, well, here's a little piece of it in yttrium barium copper oxide, for example. It went superconducting at a temperature much higher than anything had been achieved before, in particular above the boiling point of nitrogen. And so therefore, all you had to do was dip it in liquid nitrogen and it would be a superconductor, something that was not possible before then. Recently in the press, there have been a lot of reports of high temperature superconductors, but those are all under very high pressure in very, very tiny samples. So that's quite interesting. But I think this is still, I think, believe the champion is the best superconductor we still have. And it's created a lot of fundamental theoretical problems, which is what I'll talk about. So the kind of experiment you can do, you can take a little piece of it and put it in liquid nitrogen, which is, I think, sitting somewhere there. And then you can float it above some magnets, so something you can do in a classroom. And when it heats up above the boiling point, then it's no longer a superconductor, and then it falls down. So that's one of the main properties of superconductors, the abilities to, first of all, carry current without resistance, and second, also to expel magnetic fields, the so-called Meissner effect, and that's what's responsible for this phenomenon. So, of course, over the years, in the last 3 decades and more, people have searched for many practical applications. People talk about long-distance power transmissions, various kinds of superconducting MRI, things in MRI machines. But probably the killer app, if there's ever going to be one, is the application in fusion energy. That's come about only in the last few years. And there are many companies now trying to use high-temperature magnets. They could just call them HTS magnets. And they use, in fact, yttrium barium copper oxide. And so there's been a lot of technology development, and that little piece of ceramic can now be put into big wires like this. That's the superconductor. And because they require much higher temperatures and can expel magnetic fields very efficiently, this allows fusion to take place in a completely different operating point. And so this, the size of this is just a few feet, unlike the usual fusion reactors, which would fill the entire room. And let's see. Okay, so if this works, then I can justify all the work we've all been doing. But and it's certainly more likely than quantum computing. Sorry. Okay. Anyway, so here's to get to the details. Here's a very complicated crystal structure, but fortunately we won't need too much more about it. And this is a phase diagram, which is as a function of hole doping, which is controlled by changing the concentration of oxygen and temperature. So the most important sector of this, for which I'll go to discuss, is a lattice of copper atoms. So you just need to consider copper atoms on a square lattice. And in fact, even simpler than that, on each copper atom, there is one electron that's important, and that sits on these dx squared minus y squared orbitals that you see here. So in the so-called parent compound, with doping p equals 0, there's exactly one electron on every site, and these form an antiferromagnet, where the spins polarize in like a chessboard. This is called nail order. And this has been well understood and also studied a great deal. And, it's still a novel state, but there's no, as far as I know, any deep mysteries left on the structure of this antiferromagnetic insulator. Similarly, on the large doping side, when you put in, remove a lot of the electrons, so you have a large density of holes, then you get, again, a very familiar state of matter, which we'll call an ordinary metal, which would be similar to copper or gold or any aluminum or something like that. And for these metals, we can describe them by a theory that really goes back to the very early days of quantum mechanics, soon after Fermi statistics and Bose statistics Bose statistics was 1924, Fermi statistics was 1925, and then Sommerfeld made the simple assumption that you can think of a metal just as a free gas of fermions. So a free gas of fermions at low temperatures will just occupy, consistent with the exclusion principle, all the low energy states. So if you have a free gas in a metal, the states are labeled by momentum. So you just have to tell me which states are occupied and which as a function of momentum. So this is actually a plot done by a photo emission experiment. These are the momentum axis. And this bright line is the boundary based on the way they measure it and the way they plot it between the empty and the occupied states. So this boundary is called the Fermi surface. And if these were just free fermions, you would occupy, in this case, all the states inside the Fermi surface. This has this peculiar shape because of the nature of the lattice. And these states over here are empty. Okay, so that's for free fermions. But there is a very deep theorem in condensed matter physics, which will play a fundamental role in things I will discuss, called the Luttinger relation, going back to 1960, which says that if you turn on interactions, the electrons do interact with each other, the shape of the Fermi surface can change, but the area in 2 dimensions, this area here, will not change. It's the same as the area for free fermions. So that's a very fundamental theorem which has been observed to hold to high accuracy in almost any metal, and was also observed to hold here in high doping. Okay, so that's the parts that are understood. Oh no, yeah. Okay, so now there's also a theory of superconductivity due to Bardeen, Cooper, and Schrieffer in 1957. And its basic ingredient is that you start from a free Fermi gas, similar to the theory of Sommerfeld, and for some reason the electrons bind into pairs. And pairs of electrons behave like bosons, and you can think of a superconductor as a Bose-Einstein condensate of pairs of electrons. So this is not the way BCS phrased it in 1947, because things were not understood that well at that time, of course. But today, these statements are correct statements, even though you may still find books which question this, but those are books from a while back. This is still it's correct to think of the BCS theory as just a Bose-Einstein condensation of fermion pairs, sometimes called Cooper pairs. All right, so you can try to apply this theory here, and it kind of works. It gives you, in fact, it predicted in some very nice work of Scalapino the nature of the superconductor. It turns out the fermion pairs are in a D wave orbital angular momentum, and that's what this theory predicts. And they're paired because of the exchange antiferromagnetic spin fluctuations, and that leads to exactly the type of superconductor that's observed. It gives you, no one's really, the TC here, however, near the ordinary metal is rather low, so you haven't really addressed the most, the elephant in the room. How do you understand there's a very high TC over here? Okay, so to do that, you really have to start with the metal up here, and as you can see from the suggestive shading, these are not well understood metals. So that's what my talk will be about, the pseudo-gap metal, where we will have to go significantly beyond the theory of Sommerfeld and introduce modern concepts of spin liquids. And in fact, the pseudo-gap metal, as I'll argue, has entanglement, many particle entanglement, similar to that of a spin liquid. And then there's also the strange metal, which has a somewhat different type of many particle entanglement. That'll be another part of my talk, if I time things correctly. And it's similar to that in the SYK model. So what I'm claiming is that, we are now, after 30 plus years of work, really, we think we are starting to understand these rather mysterious phases of matter, and some very subtle types of entanglement are the reason it's been so hard to understand what's going on. And then, of course, once you understand these phrases of matter, then you can answer the big question, why is TC so high? But okay, we're not there yet. All right, so let's talk about some simpler situations. So one of the things that's happened in the last 30 plus years is that in some simpler situations, in particular in insulators, we now have both, it seemed like a very good theoretical understanding of entanglement in phase of matter called spin liquids. There was no theory of this in 1987, essentially. And some very sophisticated theory has been developed since then, which is also deeply connected to ideas in quantum error correction. So there's been a remarkable interplay between people studying quantum matter and people studying quantum error correction. I won't talk about that, but I'll briefly mention it. Okay, so what I want to introduce by pictures is the very simplest type of spin liquid, which has people now call the Z2 spin liquids for reasons you'll see in a few minutes. So let's go back to really the beginnings of entanglement, which go back even in some sense, even before the introduction of quantum mechanics in 1865. Kekule was a chemist thinking about the structure of benzene. So in this very simple picture here, we're just focusing on the bonding between the PZ orbitals. These are the orbitals of benzene, of carbon. These are the carbon atoms coming out of the plane of the board. And so there's one electron on each carbon atom, again, suggestively similar to the one electron on each copper atom that on the square lattice. And chemists said, well, this PZ orbital can form a bond with one other PZ orbital. They just knew something about bonding, even though they didn't know quantum mechanics. So if you think about benzene, there's two different ways to make that bond. And Kekule, in his dream, said, well, maybe it's really both. So this is what he called a resonance between two different bonding configurations. So I want to think about that as an entanglement. Today we'd say that's entanglement. And in a very simple picture of the chemical bond, in some limit where the Coulomb interactions are very strong, this is really what a chemical bond is. You have one electron here and one electron there. So the electrons don't actually move. Nothing is moving, but they form this valence bond, this particular bell pair or entangled states of their spin. And there's two possible ways of making bell pairs, either this way or that way. Oops, or this way. And really, it's the sum of the two. Okay, that's the ground state of benzene in some limiting regime. And the nice thing of taking the sum of the two is that you don't break the symmetry between the two different configurations. And then the ground state is a perfect hexagon. So that's what's pleasing. If you picked one or the other, benzene would not be a perfect hexagon, because then the bonds that are, where the valence bond is will become smaller, because that will lower the energy. So it doesn't do that. It is a perfect hexagon, we know today, of course. And so this was, we'd say, the start of multi-particle entanglement. Okay, so the next step happened in the 70s, where Anderson started thinking about antiferromagnetism on this triangular lattice. So around the same time, just a few years earlier, antiferromagnetism was discovered experimentally and then understood theoretically, discovered by Néel. But that was on the cubic lattice, or some very nice lattice. So what's an antiferromagnet? Well, antiferromagnet is, again, a collection of electrons which don't move. They're completely stationary, so it's insulator. But their spins do interact with each other with this exchange interaction, which has a positive sign. So there's spin a half. Now, these are classical spins. They form, this would be the lowest energy state. And now, in the square lattice or the cubic lattice, that is indeed what happens. You see the lowest energy state, which I showed you earlier. This state is perfectly fine, because every downspin has upspin at its nearest neighbors and vice versa. So every bond is classically just perfectly minimized. But on the triangle lattice, you can't do that. And so they make a compromise and make this 120-degree angle with each other and in the classical large spin limit. But if for spin a half, Anderson proposed, well, maybe it doesn't do this. And it forms, just like benzene, each electron forms a singlet EPR pair with some other electron. And just as in benzene, there's only one other electron you can do that with. And here's one possible configuration of the singlet bonds. You can see that this is just a dimer covering some of the lattice, which I call D. And now the big difference from benzene is that this, benzene, there were two possible dimer coverings. Here, there's actually a exponentially large number. Exponentially large in the size of the system. So e to the 10 to the 23. That's how many dimer coverings you have for a crystal. And the claim is that the ground state is just the superposition of all of them. That they're all present, just like in benzene. But now it's a sum over e to the 10 to the 23 configurations, which is impossibly huge. Much, much bigger than the number of, atoms in the universe. So you can't even write them down. Okay, so these are some of the small fraction of those. And then, of course, there are these coefficients here. And these coefficients are determined in a way that minimize the energy. And in some very loose sense, all of the work over the last 30 years is sort of classifying and understanding these coefficients. And you can also have singlet pairs within not just nearest neighbors, but longer range. And so each one of these states is a potential, what we call a spin liquid. Today we have, I think, a fairly complete understanding of the different classes of spin liquids. Certainly in this proposal in 1974, there was only this one paper, which was not commented on by anybody until the discovery of the cuprates, by Anderson himself said this is important. He was correct, I think, in that brilliant claim, which was made in Bangalore, I believe, at a meeting. But since there was no actual theory of these states at that time in 1987, it took a while, and I think we're still not there to really understand what happens. But today, I think, we're almost there. Okay. Yes? Yeah, they depend on everything. So, in fact, it would be very hard to know all the coefficients because there's e to the 10 to the 23 of them. So there isn't a computer in the universe to even store those numbers. So we have to understand roughly some qualitative properties of these coefficients. And I'll show you, the language of quantum field theory and gauge theory turns out to be the way to think about the values of this coefficient. And they definitely have a certain rigidity, which is really crucial. But yeah, so I'll give you some flavor of how that is all done. Of course, yeah, you're right. In the early days, what people did was they wrote down this is a variational wave function. They put the whole thing on a computer. They minimized the energy and got the coefficients. Yeah, okay, people still do that. But I think there's much more sophisticated analyses today. Yes? No, well, they're not in the ground state. So I'll come to unpaired sites in a minute. But in the ground state is a spin zero state. You just make a spin zero by taking this sum. This is really the most general spin zero state. So this is a basis. The dimer coverings are a basis of all possible spin zero states. It's in fact an over-complete basis. Yeah. All right. So what is what is really special? So this was really in some ways the first, what we call a quantum state with long-range entanglement. That's one way to say it. And many, many states have been discovered since then, most prominently the fractal quantum Hall states, which also have long-range entanglement. What is the key feature? What is really, you hear about topology, you hear about this and that, and all kinds of fancy math. All of that is, I think, not the key is what I've written here. It's a very simple thing. And the point is now from this state, you want to create some excited states. Now, in any other many-body system that we're familiar with, how do you create excited states? Well, you move an electron from an occupied state to an empty state. You just take some local operation and move an electron from here to there or something. Or you flip a spin, or you send a beam of light and you create an excited, you create the first excited state. It could be a spin wave or a plasmon or something, okay? So here the point is, yeah, there are actually very simple excited states which are quasi-particle-like. They have a particle-like nature. But the key point is that you cannot create them by a local operation. They actually fall into different sectors, and you can't go from one sector to another sector by any local operation. Sometimes these are called super selection sectors. So what happens then is I show you the simplest example. What is the simplest excited state? Well, you can come in from the singlet bond and just flip a spin. So that's a local operation, you flip a spin. But as you see from this configuration, if you flip a spin, you create two upspins. Okay, so now what you can do is separate them infinitely far away. And so in this region here, you have a spin and a half floating above the ground state. And that's really the elementary excitation. The elementary excitations are these particles here, which are spin and a half. But there's no way, there's nothing I can do to create just one spin-on. I mean, the only way to do it is to create two and then move them far apart. So that's a highly non-local operation. To create a spin-on on its own, I have to do something very non-local. And that's really the fundamental new property of these states, which, and it's a consequence, is another way of saying that the ground state itself has this incredibly complex configuration of entangled singlet bonds. And the rigidity of the ground state allows you to these different sectors, which are really, so the one spin-on sector is totally decoupled from the ground state. You cannot go from the ground state to the one spin-on sector by any local operation. That's the fundamental property, and today, of course, there's a huge library of such states, and I think in 2D it's all very well understood. In 3D, it's still ongoing progress. The possibilities are even much, much richer, in fact. But it's mostly a mathematical exercise because there aren't that many examples of these kind of states in nature, yeah, in 3D.
Move these apart.
Yeah.
You grab the fact that you have all these various configurations in ground state and
Yeah, so I mean, this is a single spin-on. If I look here for the single spin-on, it's this spin-on is also moving around, and all the dimers are also still resonating. Everything is present, but it's still, if you were to look at it, it looks like a completely translation invariant state, apart from a little region where you have a spin and a half floating around. So it's like a particle in every sense of the word, except that you can't create a particle on its own.
would they tend to move apart?
Well, that's the question. So if they move apart, if they can move apart, in principle, then you have a spin liquid. If they are forbidden to move apart, then you don't have a spin liquid, because then the lowest excitation is a spin 1 excitation. So it could be that these two always stay next to each other. Then it's not a state with long-range entanglement. It has no fractionalization. That's what we call a trivial state, which is all of solid-state physics for some mathematicians, yes. Yeah, but if this happened, so that's really what theory Anderson did not show, was that such a state, first of all, was stable, and furthermore, that the excitations could be separated infinitely far apart, and that's actually what you have needed a theory of the dynamics to show that. And so I'll mention this here. I believe, we were among the first to show that particular fact. No, these are all ground state, zero temperature properties, and low-lying elementary excitation above the ground state. there is, I mean, a state with or without fractionalization can be smoothly connected. There's no phase transition between them.
The excitations that you have when you're talking about these
Yeah.
going apart, they're just at the same energy, right? I mean, so is there an energetics that's involved in separating them, or is it
There could be
the same first excited state which has there are many
Yeah.
first excited states?
Yeah, so here I'm giving you an operation to create a state, but there is, if I wasn't worried about how I created them, I would tell you the first excited state is a spin-a-half spin-on. It has certain energy, it has a certain dispersion, which is all very precise. And in principle, you can measure that in experiments, as I'll discuss a little bit. Yeah, so this spin-on, when it's infinitely far away from this one, will have exactly the same properties. Now, of course, there could be a barrier to creating it and so on. So, yeah. I mean, the people, what's been a very productive mathematical approach is to classify such things. And the people, mathematicians who do it, they don't even have a Hamiltonian. Every energy is either 0 or infinity. And, but no, I don't work. I'm not that abstract. We try to put in some numbers. But anyway. All right, so this state has another very interesting excitation, which is sometimes called a Vizon. It's sort of like a vortex, and it's the following state. So remember, I told you the ground state was the sum with some CD of all possible dimer coverings. So now all I'm going to do to create this Vizon state, which is an excited state, it costs some energy to create this state, is to multiply these CD by this phase factor, -1 to the ND. And so what is this phase factor? Well, it's illustrated in this figure. You pick a point and you draw some arbitrary line out to infinity. So again, it's not a local operation. You have this branch cut, if you wish, going off to infinity. You can put this branch cut anywhere. And then you count the number of dimers that are crossing this cut. So in this case, there's just one of them. So ND is the number of dimers crossing the red line. So here's 1, and that's 1, and that's 1, and that's 2. So that'll be +1 for that configuration, and so on. So you look at e to the 10 to the 23 configuration, and for some of them, you change the sign. This is a ansatz. Of course, you can do more, but you end up with a state, which you can show is an excited state. You don't know the exact wave function, but you know it's stable. That is, once you've created it, it can't disappear. I mean, that's also true here. If you look at the spin-on, once you have the spin-a-half all on its own here, you can't get rid of it. Nothing you can do can get rid of it, because if you got rid of it, you'd be in the ground state sector, and we know there's no local operation between the ground state and the first excited state. Similarly here, once you create this Vizon, you can't get rid of it. The way you create them in pairs, and you move them apart, and they're connected by this branch cut. Okay, so that's another excited state of this. So this was slowly discovered in the late 80s, early 90s. And then in 1990, we gave a theory of this state and proved that it was stable. And it's now called the Z2 spin liquid because its stability was equivalent to this stability of the deconfined phase of a certain gauge theory. So I won't go into those details, and in this gauge theory, there were a bunch of excited excitations. I've shown you the two of them. I've shown you the Vizon, which turns out to be a boson. And then there's the spin-on. I've shown you one spin-on, but there turns out to be two possible spin-ons. One is a boson, the other is a fermion. And why is that? Well, it's related to the strange things that happen when you move these particles around each other. So it turns out the spin-ons and the Vizons are mutual semions. This means that if you have a Vizon sitting here, and you create a spin-on, let's call it the E spin-on, and move it around a Vizon, you'll pick up a minus sign. And why is that? Well, it's obvious, it's because of this -1. So when you move it around, you have to cross the cut once, and you pick up a -1. It's really as simple as that. And then there's this amazing fact that you make a bound state of a spin-on and a Vizon, and if the spin-on E was a Fermi boson, then you see that you move it around and there's exactly one cut. And that state is the same as the original state. It's like an exchange. You pick up a -1 when you exchange this bound state. So that's called the epsilon particle. So that was the structure that came out of our work in the early 90s of this particular state. And then in 1997, there was Kitaev's toric code, which was an exactly solvable model, which had exactly the same structure. So now people believed it, although we knew it was right in 1990. And now this is just the simplest example, this kind of statistics and set, so these specification here that is summarized here of the statistics of various quasi-particles or superselection sectors is what's called a unitary modular tensor category. And don't ask me what that is, but anyway, there's a very sophisticated mathematical way of classifying all of this, and the Z2 spin liquid is the very simplest baby version of different categories of these spin liquid states. Okay. All right, so now let's get to the real world. So that was in the early 90s, but it's only now in 2000s, 2020s that we are starting to see some really reasonably convincing experimental realizations. So in particular, there have been a couple of experiments on this particular compound, which has an alkali element, sodium or potassium with YbSe2. The terbium ions are spin a half, and they form a triangular lattice. It's a layered triangular lattice, but you ignore the coupling between them. And if you look at the potassium compound, that in fact has the 120-degree order in its ground state. But if you do neutron scattering, this is a picture of the neutron scattering in the experiment, and this is a modeling by SB theory refers to Schwinger bosons, which are these Schwinger bosons are just the spin-ons. So what you find from the modeling is that, yes, indeed, at low temperatures, it looks like an ordered state, which does not have fractionalization. But if you look at the excited states, that are actually better above some energy scale, it's much better described by a gas of spin-ons. So why is that? Well, these excited states have a lot of width here in energy, and that's the feature telling you that when a neutron comes in and flips a spin, it creates not one particle, but two particles. So if you conserve energy and momentum, and if I only tell you the total energy and the total momentum, which is what happens in neutron scattering, you can get, for each momentum, you can get a wide range of energies created in a given new spin flip process. And you can compute the matrix elements for all of those. That's what's done in this theory here, where you're using spin-ons to get these continua, and that's what it matches pretty well. And finally, of course, as you see from here, there's this sodium compound, which in a very recent preprint has been studied, and what they see is, in fact, a spin gap, indicating that it is indeed a spin liquid. And so this is from their paper, which I was just very, very happy to see finally. A gap spin liquid is the most natural explanation. All right, let's see. Let's see if this actually gets published, and then I can celebrate. Okay, but another direction connected to work here is in these Rydberg quantum simulators. So these are not spin systems per se, but they're a bunch of atoms which you can trap by optical tweezers. And each atom has two states, the ground state and the Rydberg states. So this is B is the operator that flips you from the ground state to the excited state or vice versa. And then when they're in the excited state, so N sub L is the number of excited states, N sub L measures the number of Rydberg states, there's a very strong repulsion between these states. Okay, so this is not this kind of spin system I was talking about, but as was shown, especially in the work of my former student, Ryan Samajdar, on certain lattices, it can form rather exotic states, including a particular spin liquid state. Okay. So there was, I just mentioned this particular experiment, where this configuration was proposed by Rubin Verison and Ashwin Vishwanath. where they put Rydberg atoms with optical tweezers on the bonds of the Kagome lattice. And from their observations, there's some evidence, this is not conclusive, that the ground state of this system looks something like this. That is, it's, in principle, if there's a big enough system, it's e to the 10 to the 23 configurations. Well, this is about 200 atoms, so e to the 200 is still pretty big. And now each configuration is not labeled by a valence bond, but by a Rydberg state. So the big circles are the Rydberg atoms, the small circles are the ground states of the atoms. And the basic point is that the Rydbergs don't like to be next to each other because they repel each other. So the big circles like to spread out, but you want to put as many big circles as possible because that's what the pumping is doing for you. And so it's very much like the dimer covering, where you want to have a exclusion principle that no, you can't have two dimers on each side, but you want to close pack. So you want to close pack the Rydberg atom is consistent with no nearest neighbors, and that's identical to the constraint of dimer coverings. So this is essentially the same spin liquid I showed you, but realized in a very different way on the lattice. Okay. All right, so that's all great for the triangular lattice, and if this all applied to the square lattice, the high TC problem would have been solved, in my opinion, long ago. But the square lattice spin liquid turns out to be much more complicated. I better keep track of the time. Okay. So here's a relatively recent numerical study of the square lattice antiferromagnet with first and second neighbor exchange interactions. And as a function of J2 over J1, for a wide range of J2, you get the state that you actually see. But eventually you get this valence bond solid state, this green region, where the singlets crystallize in some configuration like this. But there seems to be some spin liquid in between, and this spin liquid doesn't have a gap in all the numerical study. There's something that's really in some ways more complicated than the Z2 spin liquid I just described. And in fact, it's quite similar. So there's a huge amount of work here that I'm just skipping over. But the picture that's emerging is not so different from our paper in 89 and 90, where we use this parton representation of the spins in terms of these bosons, which then become spin-ons if they're free. And in this case, on the square lattice, they're coupled not by a Z2 gauge theory, but a U1 gauge theory. So you basically have a relativistic field theory of these bosons, the Z alpha, coupled to a U1 gauge field. So it's really quantum electrodynamics, but with bosonic matter. Okay, so we understand quantum electrodynamics, so what's the big deal? Well, it's not quite quantum electrodynamics, it's quantum electrodynamics with monopoles. Now, the electrodynamics in our universe also has monopoles in principle, but they're very, very heavy monopoles at some grand unification energies. We think. Nobody's ever seen them. So they're not important for anything we do in the observable universe so far. But here the monopoles are very light because of the nature of the lattice structure. And so these monopoles are actually extremely important. And what we showed was the way they act is to destroy the spin liquid. And you get this valence bond Allred stiff. So the question you asked, can you separate them far apart? The answer is, in this region, you cannot. It's like two quarks, they're confined, even though the gauge theory is U1. But nevertheless, there seem to be some gapless spin liquid right at the boundary, and this is roughly consistent with what's being seen in numerics. They certainly see the valence bond solid we predicted and this gapless spin liquid. Yeah, I could spend the rest of my time just summarizing all the work that's been done on this since then, but I won't. Let me just mention the experimental relevance. So one place where something like this is now starting to be seen quite clearly is in not quite the square lattice, but what's called the Shastri-Sutherland lattice. And in this compound, strontium copper borate, Again, the copper atoms form a square lattice. It's a diluted square lattice, shown by these arrows here. And they're coupled by these bonds. And at ambient pressure, then these bonds just form singlets, and that's kind of a trivial exact round state found by Shastri and Sutherland. But as you apply pressure, you see this valence bond solid, which was also theoretically predicted. And then eventually, presumably, you get the nail order here. So you get this nail VBS transition, and people have been studying this, and it's very, very similar in experiment and theory to what was predicted for the square lattice. But okay, so finally, let me return to the problem that motivated all this 30 plus years of work. So what does this have any relevance to the cuprate high temperature superconductors? So I want to make the case that it does. And let me do it, just summarizing the key facts. There's a whole long series of discussions here, but I'll just talk about the simplest and most important fact. So now what happens when you look for the Fermi surface here? I showed you the Fermi surface here, and the short summary is the Fermi surface here is just as that for free electrons. So Sommerfeld was basically correct from his 1927 theory. But if you look here, what you see is that the Fermi surface is not anything like that. It seems to be this small pocket Fermi surface. Here's one theory of it, and there are many others. And the most striking feature of this Fermi surface, it doesn't obey the most fundamental theorem of solid-state physics, which is the Luttinger theorem. Recall I told you about this theorem. It says that the volume enclosed by the Fermi surface is exactly the same as that for free electrons, no matter how strong the interactions. So here that's violated. And of course, all this work on spin liquids now showed us, in fact, how can that happen? Well, so when you look at the Fermi surface and you look at the volume enclosed, a bunch of holes, not electrons, are actually missing. But let me imagine they're electrons. Where are the missing electrons? Well, the answer is the missing electrons are in a spin liquid. So that's a simple way of saying actually a rather deep theorem that's come from all these topological arguments. And the starting point was Oshikawa realizing that actually the Luttinger theorem is one of those things, deep theorems of the 21st century that was discovered in the 1960s. Today we understand the Luttinger theorem as a very fundamental statement of a certain anomaly in a topological phase. So from that, we can now see that, in fact, you can violate the Luttinger theorem provided you have a spin liquid in the background. So to us, the photoemission experiments immediately says there's a spin liquid hanging around. So where is it? All right, so of course, I got that question a lot. But just a few months ago, I was talking to Stephen Hayden, and he showed me this data that he measured a few years ago, which is very striking. So this is resonant inelastic X-ray scattering. I don't need to go into details. But if you're at x equals 0, meaning the antiferromagnet, you see a very sharp line as a function of momentum and frequency. And that's the spin wave. That's the antiferromagnet. Everything is great. But if you dope the system, you see equal intensity. The spin wave doesn't disappear, but it's all very broad. Okay? So this broad continuum is, again, we would claim evidence for spin-ons, because neutron creates always spin-ons in pairs, and if you only fix the total momentum, then the final energy is not fixed. And so you can get for each momentum, you can get a whole continuum. All right, so right now we are working on some calculation to fit the data. We're optimistic, but I don't have to show you how that works. But I think this is pretty striking evidence for spin-ons, just as for spin liquid, just as required by the Luttinger theorem. All right, so that was the first part of my talk. So I have about 15 minutes, is that right? Okay, great. So that's enough. So now I want to talk about the strange metal. And so here, I mean, a spin liquid, as I've showed you, is sort of entanglement of of insulators. The electrons are not actually moving in the spin liquid. You know, what's moving as the bonds are resonating is, if you wish, the entanglement or the quantum information. There's lots and lots of state which are different patterns of entanglement, but nothing is actually moving. Okay, the spin is zero everywhere, charge is zero, but it's some mess of resonating entanglement. But to understand the strange metal, we need another paradigm, at least I claim, where you have to entangle mobile electrons. You have to entangle things that move around, fermions that move around, as in the Sommerfeld theory. You still have to let them move around. I mean, what happened to pseudo-gap is some of them move around and form the pocket, but the others are stationary and form a spin liquid. And there's very precise theoretical ways of setting all that up. Okay, so I want to talk about the strange metal. So let me just quickly summarize what is, again, the key strange property of the strange metal. So the fundamental Sommerfeld theory, which of course became much more of a theory, work by Landau, who applied the Boltzmann equation to Sommerfeld's theory. And from that you conclude that the typical scattering time of electrons diverges as temperature goes to zero, as 1 over temperature squared, and the resistivity must be a t-squared dependence on temperature at low temperature. And all of this is self-consistent, provided tau is much bigger than this time that you can make out of Planck's constant and temperature and the Boltzmann constant. So this is sometimes called the Planckian time. And you see that as temperature goes to zero, the theory says that this will diverge as 1 over temperature squared, this will diverge as 1 over temperature, this is always shorter than that, and so the theory is perfectly fine in any metal. So that's why it was quite amazing. For example, in this recent experiment of optical reflectivity, again, I won't go into details, they measure tau of omega. So this is omega is the frequency of light, and tau they measure at different temperatures. Here's the results for different frequencies and temperatures, but it's summarized here. It's in fact just the Planckian time. And this scaling works beautifully. So it seems like there's a total breakdown in a very fundamental sense of the basic theory of Sommerfeld, Landau, Boltzmann. Okay, so that's the strange part. All right, so how do we, so I'll quickly summarize some of the things that have been learned. And at least my own work is very much based upon a solvable model of quantum entanglement, where we have entanglement of mobile electrons, not stationary electrons, which is what spin liquid is about. So like Kekulé, I claim I had a dream of snakes moving everywhere. So that's just a very simple summary of the model. So you imagine you have a bunch of sites, 18 sites here, and you put electrons, for now assume spinless, on some fraction of the sites. And now these electrons are going to move around, because I want a mobile system of fermions in a strange metal. But they're going to move by, just put one restriction. So at the time we proposed in a somewhat different model, there was some rationale for it. But now let's just view it as a mathematical tool to get an entangled ground state. So they're going to move always in pairs. So for example, there's a process where electron 11 and 12 will move to sites 5 and 14. So every such process has a number associated with it, which depends on every little detail of the problem. So any set of multiple electrons moving around like this, you have to give me a list of these numbers, and then I have to put the whole thing on a computer and solve it. Except that the number of configurations is exponentially large, so it's almost impossible. So what we pointed out was that this complicated problem can be solved with one simple assumption. Just assume these are independent random numbers. That's all. Once you know the independent random numbers, it turns out you can make enormous progress. So here's the actual model if you want to see it written down. So there's an ensemble of Hamiltonians where these u, alpha, beta, gamma, delta are independent random numbers. But the amazing thing is that this problem is self-averaging. So for almost any property that you measure, you just need one random configuration. That's it. That's enough to give you, it converges, it's a champion of self-averaging because the size of the Hilbert space is so huge. Okay, so now I won't go into how this is solved. There's a set of standard many-body tricks by which we solved it. When we started working on it, surely somebody has solved this before. Nobody had done it, and it turned out to have some very interesting properties. So let me actually, just to highlight what's remarkable about this problem, let me talk about a simpler problem. So let's take the simpler problem where the electrons can move one by one. So there's some hopping matrix element for each site, Tij, and we just take Tij to be a random matrix, n by n random matrix for n sites. Now, of course, we know everything about random matrices. This is a random matrix. They have a famous Wigner-Dyson semicircular density, Wigner semicircular density of states and Wigner-Dyson statistics of individual energy level, whose spacing is about a 1 over n. And the ground state is you just occupy the lowest n states, and Q state. Q is a fractional occupation. And then the entropy vanishes as temperature goes to 0, linearly in temperature. That's the famous Sommerfeld result from 1927. All you need is the density of states at the Fermi level. Okay, so everything well understood, and even the spacing between these books have been written on the statistics of these energy levels. I want to take this familiar problem and think of it as a many-body system. So everything I was saying so far about was one electron. Let's take still free electrons, but think of the many-body eigenstates. So what are the many-body eigenstates? The many-body eigenstates are actually exponentially large. You fill any Qn of these states in the canonical ensemble, but I'll work in the grand canonical ensemble. Then there are 2 to the n states. And these are the states. You just tell me n alpha is 0 or 1 for every eigenstate, and that gives you 2 to the n states. So you take all these 2 to the n states and plot the density of many-body states. That's called capital D of E. And this is what you get. You get this, it looks like a Gaussian, but it has these very long tails. And all the fun stuff is in these tails. So when the energy is extensive, then you can just use Sommerfeld, who tell you the entropy vanished as linearly in temperature. And then you convert that to the canonical, microcanonical ensemble. You said the density of states then is E to the square root of n times E. And that's this region here. But if you look at the very bottom, so since E is extensive, this is E to the n, and so there's exponentially small spacing between the energy levels here. But if you go to the bottom, see a very sparse set of levels. And why is that? Well, because at very low energies, there are very few states. So if you want to create an excited state here, the lowest excited state is just pretty unique. You have to take an occupied state just below the green line and move the electron to an unoccupied state just above the green line. And no matter what you do, that will cost you energy 1 over n. So the spacing between the energy levels 1 over n, that tells you the density of states is order n. So you go from a density of states of order n in this tail to a density of states of order e to the n. This is just free fermions in a random matrix, that's all. Just writing it in a way that we normally don't write it. Although nuclear physicists actually do think this way. All right, let's do the same for this model. Now I can't use any free fermion description and just look at the numerical results. So what you see is the tail is gone. And instead, if you look at the bottom of the band, the energy level spacing is exponentially small. So the density of states is exponentially large. And this was a result that we obtained in 2001. And this means, so it's exponentially large here, it's also exponentially large there. And today we also know the full crossover function. So this means that this system has a non-zero zero temperature entropy. Okay. So to summarize, from the work on this model, we found that it indeed had this tau of omega, which was of order h bar over omega temperature times some function of frequency and temperature. So that got us very excited. We were onto something. And then we discovered this very strange feature, that the entropy, as temperature goes to 0, is extensive. Okay. So we said there's no absolutely zero experimental indication that this is the case in the cuprates. So we said, okay, we don't like this. We put this in an appendix of this paper and then moved on to other things. Because this really wasn't a very good result as far as theory of strange metals were concerned. Okay. But historically now, this was one important point here. As this picture shows, you can get a zero temperature entropy without actually an exponentially large degeneracy of the ground state. In all previous examples, the only way you violated the third law of thermodynamics was having a hugely degenerate ground state. That's not what happens here. It's a generic model. You take these random couplings. The energy level spacing is exponentially small, all the way down to the ground state. And that's what leads to this zero temperature entropy. It's not the same as a ground state entropy. It's the zero temperature entropy. And that has to do with this order of limits mentioned here. I'm out of time. Okay. All right, very quickly. So anyway, we got some rather bizarre model of multi-particle entanglement, where we could say that if this was actually happening in the world, you'd get a first example of a solvable model where a current was carried not by electrons, but by some entangled quantum soup. Okay, can I have 5 minutes? So, in around 2010, I suddenly got interested in the model again after a gap of about eight years, because then I learned something about black holes. And then I learned that there was this huge puzzle in the theory of black holes, which is exactly what our model seemed to be designed to solve, although that was never the intention. So what are black holes? Well, we had a nice talk yesterday of black holes. These are regions of space-time which are very dense matter, from which light cannot escape. There's a spinning black hole at the center of every galaxy, including our own. And in Einstein's theory, because gravity is always attractive, even after a black hole forms and there's a horizon, the matter continues to collapse into a site of infinite density at the center of the black hole. So when there's an infinity in the classical theory, surely you have to do a quantum theory to understand what's inside a black hole. Okay. Then moving on, we come to Hawking in 1975 or so, where he started thinking about quantum theory of black holes. We're still a long way from understanding what's inside a black hole, but Hawking's great insight was, well, let's look at a black hole from the outside and ask if there are any quantum effects. And indeed there are, and they can be summarized by this fact that if you take an entangled pair and one half of the entangled pair falls inside a black hole, then that's allowed. And this will happen spontaneously by quantum fluctuations. Then if you're safely outside the black hole and you have this one half of an entangled pair in your hand, this bit is completely random because there's no way you can access what the other bit is doing. It's outside your observable universe. It's behind the horizon. And so this bit is random, and as Boltzmann taught us, randomness equals temperature. So, okay, I already said that. So this sets up, you can call the battle of the gravestones. Boltzmann gravestone says entropy is log of the density of states. And Hawking's gravestone, well, it doesn't quite have this equation, but has a closely related equation, that the entropy is proportional to the area of a black hole coming from this entanglement across the horizon. So if entropy is equal to this and equal to this, what is the D of E for a black hole, and what states are we talking about? Okay, yeah. All right, so coming back to connection to the SYK model. So what was known, and this is something I only discovered around 2010 or maybe a few years earlier, that if you look at any dynamical properties of a black hole, they're also Planckian, that the characteristic ring down time or various normal modes of a black hole have a damping rate, which is just h bar over the Hawking temperature. So that's exactly like the XYK model. And then, I remember the day I realized this was my very exciting day. They also have this other unwanted property of the SYK model. It is, in fact, the property needed. They also have certain classes of black holes, charged black holes or rotating black holes, have an entropy in the 0 temperature limit. So charged black holes, as you go to 0 temperature, have a finite area, which is just related to the charge and the Newton's constant and the velocity of light. And so because they have an area, and by Hawking's arguments, area equals entropy, and therefore there's a 0 temperature entropy. So this was already in Hawking's paper in 1976. So he was, but it wasn't until 2010 that I heard about it. And there have been a lot of work, and this also applies to rotating neutral black holes. Many papers have been studying recently. But what the SYK model now shows, which was not, I think, not understood before, was in previous string theory calculations, the way they understood this was actually having a hugely degenerate ground state due to supersymmetry. But now we don't have any supersymmetry or anything like that. That's not present in our universe at low energies. And so now we know from the SYK model, there's no need to have a degeneracy. You just need a very complicated entangled state. And that will give you a 0 temperature entropy. All right, so this is the start of a lot of work. Here's one major result that's come out of it. Nothing directly mine, although I pointed the way. This is the density of states of a black hole. So now we know the answer. This exponential factor was the Bekenstein-Hawking result. And then the cinch is basically this envelope here that came from a theory of the SYK model, all the constants you can fix. And then there's a prefactor that's not related to the SYK model, which is different for the SYK model, only recently in some work of Luca Eliasiu, Samir Murthy, and Joaquin Turiacho. So the bottom line, and I'm way over time, that the SYK model simulates the low energy properties of the interior of a black hole for an outside behavior. That's not to say that actually SYK model inside. From the outside, you couldn't tell the difference at low energies. So we have also now, of course, what about the original elephant in the room, which is the strange metal? I have no time to tell you about this, but Avishkar Patel, who's I think visiting ICTS right now and will be around. So I've been working with him and several other wonderful collaborators to extending the SYK model to something that's much more realistic for the cuprates. And the key is to think about quantum phase transition in the presence of spatial randomness, which we now learned how to do using the SYK model. And from that, we can get results that look very much like the experimental data, including this tau of omega property that I've been emphasizing. So we get the tau of omega, which, okay, maybe that's not such a big deal because even the old SYK model can get it. But we can get that and at the same time have the right entropy. That's what we've finally achieved after a lot of work. And we think we understand how to do it now in general. So let me conclude. So I talked about two different classes of entanglement. One is the entanglement of stationary and electrons. And now there's starting to be many experiments in condensed matter and also in optical tweezers of the simplest spin liquid of simplest entangled state of stationary electrons, like the Z2 spin liquid. There's some indication that the cuprates are described by this U1 spin liquid appropriate for the square lattice. That's our claim. And finally, the SYK model has given us some extensions of it, are finally making progress on the strange metal. And to my great good fortune, they also have made progress in a completely different field, which is new understanding of the structure of black holes at very low energies. Thank you.
Thanks a lot for the wonderful talk. I'm sure there are a lot of questions.
So I had two questions. So the first one, you mentioned this Luttinger theorem that's been shown that if it's violated, there's some spin liquid lurking around. But is that necessary, or it's just some long-range entanglement state has to be there for the Luttinger theorem to be violated?
Probably the latter. There's a much more precise statement that I didn't go into.
Right, but it's probably
but
just
it has to be a state with some fractionalization. I mean, there can be many. I'm equating long-range entanglement. That's kind of a loose word.
Right.
With fractionalization, that's a more precise word. So there has to be a state that on a torus has low energy excitations that are in a different sector from the ground state. You know, in a Fermi liquid, every state, even on a torus, you can build by just adding and removing particles, local operations. So if you're violating the Luttinger theorem, they have to be states that are cannot be reached by any local operator. So that's the theorem we established, building on the route shown by Oshikawa.
And I guess I can wait for other questions and then come back to my other question, if there are more questions.
Thanks again for a very nice talk. So I'm confused, however, with the black hole results.
Yes.
Because, of course, when you were talking about the SYK model, you have, particular physical model states which you know how to define.
Yeah.
In quantum gravity, we do not know what the states are. We don't know anything about the Hilbert space. Even Hawking's ideas are for quantum fields on curved space-time. So are you talking about states which are quantum fields, or are you talking about some as yet unknown quantum gravity states?
All right. So that's a great question, and I'm happy you asked, because those are the things I cut out of my slides, exactly to address those questions, to get the thing down to 1 hour, which I didn't succeed. So first of all, there are two calculations you can do. One, we can just follow the route shown by Gibbons and Hawking. So they just take the Einstein action, Einstein-Maxwell action, for a charged black hole, and they just evaluated the action at the saddle point, and they got the semi-classical answer. All right. So what's been learned now is that you can go beyond the semi-classical answer. You can also do a path integral, a full path integral of certain select low energy modes. So what happens for charged black holes is the low energy sector can be taken to the near horizon region, and so it turns out to be exactly quantum gravity on ADS2 with a dilaton. That's what you get from the dimensional reduction. So in fact, if this article here, at least from the point of this article which I mentioned, no, here, this Reviews of Modern Physics article goes through that right here. Where is it? No, that was in the black hole section, sorry. Yeah, so this Reviews of Modern Physics article goes through the full argument that I'm just now describing, if you want to hear more. And okay, so you take the low energy limit of Einstein gravity, but all you do is you take the semi-classical approximation much more seriously. You actually do the semi-classical Gaussian fluctuations. So Ashok Sen actually pioneered this approach. He started looking at Gaussian fluctuation corrections to Einstein, to the Gibbons-Hawking calculation for certain class of black holes, including non-supersymmetric one. But while he was doing it, he found that there was a certain zero mode, which was flat, didn't have any dispersion, which he didn't know what to do with. So he just kind of mentioned it and didn't work on it very much. So what's now happened is that there's a complete analog of that zero mode that also appears for the SYK model. So the SYK model, you start with the fermion Hamiltonian, you get the saddle point, and you look at the Gaussian fluctuations. And it turns out in both cases, you can start from Einstein gravity and get down to the zero mode theory, or you can start from the SYK model and get down to its zero mode theory. Those theories turn out to be identical as the Schwarzschild theory. So that was, Kitaev and Maldacena and Stanford were key people showing this connection. So So from the example of the SYK model, it was understood how to do this path integral correctly. And you could now believe the result because there were numerics, there were all kinds of hints from the SYK model that this is what you need to do. So in principle, everything, this result here, in principle, could have already been obtained by Gibbons and Hawking. Everything was there if they just bothered to continue the path that they established. So it's just a property of Einstein gravity. Everything here, certainly the cinch just relies on Einstein gravity and nothing else. This factor requires you to lower the number of massless particles in your standard model. That's what this peculiar factor comes from. Okay, so what we've learned here is that this is what in condensed matter we call a universal result. I'm not saying that there's actually an SYK model inside a black hole. I'm certainly not saying that. But what we have learned is that that semi-classical quantum gravity is much more powerful than anybody ever imagined. It actually gives you the full density of states. And at very high energy, there could be string theory and God knows what else. I'm not making any statements. But the claim is that no matter what the high energy limit is, in low energies near the ground state of your black hole, this is the answer and it can be obtained. It's agnostic to what is the high energy theory. It only depends upon Einstein gravity, pretty much. And also, I mean, there's also been now progress in the so-called Hawking paradox and the Page curve and so on. And again it's the same phenomenon playing out. These were results that could have been obtained a long time ago in principle. But there people found that semi-classical gravity, provided you do it the right way, as Maldacena described in his talk at ICTS last week. The proper application of semi-classical gravity is much more powerful than anybody really anticipated. And I would claim, that shows you what I would say is the power of having a solvable model. Because when you're just doing semi-classical gravity, you see all these infinities. It looks like impossible to solve and totally meaningless, so you don't know what to do. But when you have a solvable model, it gives you a direction. And then it was realized from the example of the solvable model, you could go back and look at the Gibbons-Hawking calculation and do it much better. Okay, so very long answer to a good question. Yeah.
So this strange metal part, you were saying SYK model explain?
No, again, I'm sorry for going through it very quickly, but there's an extension of the SYK model, which now people are calling the 2D Yukawa SYK model. I have some slides on that if you want to see them. I'm happy to show them. You want to see them? Okay, where is it? I'm going the wrong way. No, am I? I'm going the wrong way, excuse me. Let me just... yeah, so, okay. How do okay, I'll just do it the old-fashioned way. I can't really see a thing on this board. Here we go. Zoom, fit to slide. Okay. So this is you start with this theory of a quantum phase transition here. Between two possible Fermi surfaces, and you write down a theory for this, and the theory has this structure. It has a Fermi surface coupled to some scalar field phi, which is this, and this is Yukawa coupling. And then you want to put in some random potential, and you put in a random spatial dependence of the critical point, and then you realize the way to do it is actually to move that randomness from S to G. So you end up this theory with a random coupling. So the bottom line is that SYK model has told us how to analyze in a systematic way systems with random interactions. I mean, see, it sounds like a simple thing to say, and it is a simple thing, but the entire history of solid-state physics in random systems is random potentials. But now we're learning how to do random interactions. And we just apply those lessons to this theory and we get the results that I showed. So it's not quite the SYK model, but it's this, what's shown here is the two-dimensional Yukawa SYK model is what people are calling it, which I'm not objecting, of course.
No, because your strange metal is there was appearing at high temperature.
Yeah, all right. Yeah, so then if you analyze this theory very carefully, you will see the strained metal at finite temperature. Then you also see superconductivity. You also see certain Griffith's singularities, which are also observed. So there's a...
And you can study entanglement also.
I mean, I think Sumilan Banerjee is doing some work on that, theoretically. Experimentally, there are really essentially no measurement. How do you measure entanglement? I don't know. There are some experiments on quantum Fisher information, but quantum Fisher information is not really a true entanglement measure. Well, so let's go to zero temperature. Think of the strained metal as zero temperature state. I would expect some area law violation, like in any metallic system. But it's not understood.
Okay.
Yeah.
And if you try to change through this doping from
Yeah.
pseudo gap to strange metal,
Yeah.
what would you expect there?
That is
For
a
the
big
intent-
problem, yeah. So we have papers on all these questions, and that's very much a topic of research. Okay. I have a whole other talk on exactly the questions you asked, but okay.
No,
I think
I just-
I gave that talk in IIT Madras, and I think it's online. Yeah.
Okay, thank you.
But yeah, I'm happy to tell you more. But okay.
If not, I request our director, Professor Tarun Sauradeep, to present, as a token of appreciation, a few memento from Raman Research Institute.
Okay, thank you. Thank you very much. Oh, I see. Thank you. Thank you very much.
Recognizing that you are the Raman Chair
Thank
at
you.
the Indian Academy of Science.
Yeah, thank you
This,
very much. Thank you.
Pictorial biography and Computer Institute, which completed 75 years. So
Ah,
we had a commemorative stamp. So I thought you might want to
oh, thank you.
give the album.
Oh, beautiful. Okay, thank you.
This is for the Platinum Jubilee of Amar Institute. And
Yeah.
collected works of S. Pancharatnam.
Thank you.
And yeah, this
Oh.
is very interesting.
Yeah.
Really enjoy it. And this is, again, related to the Platinum Jubilee. Nature India and RRI brought out the highlights of research over the 75 years, so selected research. I'm sure
Well,
you'll enjoy that.
thank you very much. Great honor for me to receive all this. Thank you. Okay.
And I should also mention that he is the Raman Chair, so at the Indian Academy of Science, but basically part
Today
of
is
the
my
whole
last day as Raman.
Raman infrastructure here. So I'm sure he'll be visiting again, and so I was really glad to see. I mean, if you are disappointed you haven't had time to talk this time, he'll be here again, I'm sure, very soon, and then you can, book him up for the entire month or so. He'll be here. Okay, thank you.
All right. Thank you.
So thanks, Professor Subir Sachdev, for the wonderful talk. And we have tea outside at the back of the building, so we all are welcome for the high tea. Thank you very much.